Cool. Thanks everyone for having me today. So, Bazaarvoice only recently signed up with Arize, so I'm really excited to share our experience with the platform. And when Bazaarvoice picks a software vendor, we look beyond just features. We really pay attention to see if the company's value and direction fits with our own. And fit's kind of a hard thing to read, so we often dig through the company's About Us page. These are a bunch of photos I stole from the Arize About Us page. It looks like a pretty fun place to work. So before our first call, I had a lot of questions, but none more pressing than, hey, where can I get one of those hats? And finding a product computationally from an image is an AI problem known as visual search. And that's what I'll be discussing today. You might think that apparel or clothing and computing don't have a lot in common, but in fact, they share a rich history. To see this, it helps to know how clothes are made. This is probably not where where you thought this talk was going. This is an animation of how a loom works. It moves warp threads up and down and shuttles a weft thread through them. And by changing which warp threads go up and down, you can create different patterns in the fabric. And historically, patterns are what sold clothing, and making those patterns required specialized skilled labor. But then in 1804, Joseph Marquis Jacquard invented the Jacquard machine. It used paper or wooden cards to alternate warp threads that would be pulled up, eliminating the need for skilled labor. This caused a paradigm shift in textiles. Companies had to deal with intellectual property, and the competitive advantage shifted to the pattern itself instead of who was employed. The Jacquard loom led directly to Hollerith's pantograph punch used to tabulate the 1890 census, largely viewed as the first instance of computing at scale. And this pantograph was a direct predecessor to IBM's punch card computing patents. Fast forward a few years, and now we have smartphones. We still have an interesting marriage of computing and apparel in the commerce space. This is an example of visual search in Google's smartphone technology. Pretty cool, right? But such technology is a bit more complex than your typical machine learning classifier. And with this complexity comes a lot of risk. You might have read the classic paper, Hidden Technical Debt in Machine Learning Systems from Google. And visual search is no exception here. The machine learning models are black boxes. This presents a lot of risk to our business, as the value of our visual search system could drop dramatically without us knowing. In fact, ours has, and we're going to see that in a little bit. And one way to mitigate this risk is through model observability. This sounds pretty hard. How you do it? How do you understand what's going on in a model with millions of parameters? So today, I'm going to show you that observability is easier than you think by sharing our experience with Arize as a new customer. Specifically, I'll share how Bazaarvoice's visual search system works, how we measure its business value, and how observability lets us see exactly what we can do to increase that value. So a little bit about me. In 2012, I got my PhD from Drexel in computer vision and machine learning. And then I went to work for a startup, hopped out of academia, startup called Curate, where I got to wear a lot of hats. I acted as a data scientist, a researcher, an engineer. I didn't have an Arize hat, though, at the time. And then in 2020, that startup got purchased by Bazaarvoice, which is where I work now. And there I'm spending a lot of time trying to use MLOps and building out our MLOps platform to democratize AI so that all of our developers can integrate AI into their products. But enough about me. Let's get back to visual search. And to motivate why we have visual search at Bazaarvoice, it helps to understand a little bit about what Bazaarvoice does. So Bazaarvoice facilitates trust between consumers and e-commerce companies by curating user-generated content. Specifically, we provide software that lets consumers post reviews, photos, videos, and questions and answers to our clients' websites. This builds trust between consumers and brands by making the online shopping experience more transparent. Consumers know what they're buying, and this results in an increased sale for our clients. Today's talk is focused on images, so let's see an example of one of our products in this space. Our Visual Galleries product displays images from social media on our clients' websites to drive sales. Specifically, our software collects media from Instagram and lets our clients search, curate, and post those images and videos that we've collected to their websites. This product has a major drawback. For this product to work, we need to solve a key data association problem. Specifically, which products from our clients are in this piece of user-generated content. So this is our visual search problem in a nutshell. We want to be able to take a piece of user-generated content, some imagery, and figure out which products that belong to our client are in that photo. And total automation of this is extremely hard. A lot of products look really similar. Just think about blue jeans. They all almost look the same. So instead of trying to totally automate this, we're going to recommend products to our clients that we think are in each photo and let them confirm it in a UI with just a few clicks. Let's see a demo of this in action. So here's a piece of user-generated content the client wants to associate with products. As you can see, when they click Add Products, we detect some objects in the image. And then when they click the object, we show them search results from their catalog on the right there. This lets the client quickly associate any products with the user-generated image. Once finished, the image is ready to display on their website. This is the client's visual galleries where consumers can come and get inspired by the new look. The user-generated content we saw can now be clicked on, and the consumer can be taken directly to the product. So that's how our visual search product works for our clients. Let's see how it's working under the hood. So I'm going to give a rough overview of the architecture here, and then we'll dig in a little deeper. So on the data side, for our inputs, we have our user-generated image that's shown on the top, and that is what we refer to as our query image. We don't know about that until the client opens it. In addition, we have all of the images that are in their product catalog. Those are shown on the bottom. Those we'll refer to as our reference images. They're often product shots that are uploaded to their e-commerce website. On both sets of images, we start out by running an object detector. This allows us to detect parts of the image that contain specific kinds of products, skirts, shirts, pants, things like that. We then take those images and crop them and send them through a convolutional neural network. At the end of this convolutional neural network, we kind of chop off the end to get a high dimensional feature embedding that represents the appearance of that object. So here I've indicated the query image feature vector by X and the reference image feature vectors as Y. And you'll notice we have a number of reference image feature vectors. I've indicated we have N of them. That's because we have that many products in their catalog. And also you'll notice these are really high dimensional, like 2048 dimensions, so pretty high dimensional vectors. Finally, to surface the search results, we just find the closest result in that feature space. So we take the query vector X, and then we look through all of the reference vectors Y, take the Euclidean distance, and take the min of that. And those are our search results that are surfaced to our client. So each of these steps we could gain observability from using Arize and treating each as a different model. The rest of this talk will be about how we did those steps and the results we found by onboarding them to Arize. The object detection piece, I've heard a rumor that that will be released soon. So I'm not going to go into that. We haven't done that yet. That's not available in the Arize platform. But I will talk about the image embedding and the search ranking. And I'm actually going to start at the end there. It looks like a really easy problem to solve. You just take the distance and minimize it. But actually, the high dimensionality makes it really hard. In addition, our clients could have millions of products, which means like this actually becomes a problem of scale. So the general problem of finding the closest feature vector in this space is known as nearest neighbor search. Claire, not everything is a dot product. We're going to we're going to stick to Euclidean distance today. So the general problems finding feature vector is known as nearest neighbor search. And if we define this formally, if you guys will tolerate a little bit of math today, the formal problem is find the vector in the reference set y that is closest to the query vector x, where closest is defined by some distance function. Again, we're going to use the Euclidean distance in this example. So the naive algorithm is to just compute the distance between all of the feature vectors y and take the minimum results, right? This is asymptotically linear. And as I mentioned, that's not really good for us because we have millions of products. And again, there's high dimensionality. So there's a big compute cost there. There is a variant of the nearest neighbor search that we want for our product. This is called k-nearest neighbors. And in this case, we want more than just the closest object. We want the top k closest objects. So the naive solution to this is has an asymptotic cost of n log k. The idea is you take your distances, throw them into a max heap of size n, and at the end you have the top n closest, right? So this is still not great. We're still dealing with millions of records. We've just made it for worse. So in order to deal with this scale, we can move on to approximate nearest neighbors techniques. So to make it scalable, we're going to turn to approximation techniques that avoid computing the distance to every reference vector. There's a huge range of research on this, and I'll get into some of the techniques in a little bit. But the piece that's really important to us is how we measure accuracy here. So if you look at approximate nearest neighbors techniques, often one of the metrics that they use to measure accuracy is known as recall at k. This is the recall. You guys are probably familiar with that in terms of precision recall. It's the recall measured after the top k results. So if you're measuring the accuracy of your approximation technique, then a recall at k, if your k is 10, of 1 would indicate that you got all of the relevant documents in there. Your approximation is exactly correct. The easy way to look at this, or another way of looking at this, is the percent of queries with the correct answer in the top k approximation results. So this is a cool metric for us because it actually ties back directly to our business case. If we think about this, recall at k can measure the impact of the system that these models have on our clients. Specifically, if we consider the relevant objects, the products that the client wants to tag, and we say we're going to set k to, say, 5, because that's how many are shown in this example demo here, then recall at k measures the percent of time that we recommend the correct product to our clients. The higher the percentage, the more we're enabling them to send photos to their website without manually entering the product photo. So this is our key KPI measure of this system. In other words, it's the metric that we use to measure the goodness of the system is recall at 5, measured on the actual results. So approximate nearest neighbor techniques, as I mentioned, there's a lot of different ones out there. You can kind of bucket them into 4 different sets. There's trees and forest. These are KD trees, which is similar to a binary search that's done in higher dimensions. So if you're familiar with binary search, it's the same idea. You subdivide data and kind of go down the tree. And when comparing these, you can often look at like not only query time, which is shown here on the table asymptotically, but they'll often compare accuracy as well. But one thing that most often isn't compared that mattered a lot to us was the storage cost of each of these different techniques. I have a whole nother talk on this. If you check out my website, you'll see some of them, or I'm happy to give it again at some point about why storage costs matter and how we can reduce that. So you'll notice that out of these techniques, the one that has the best storage cost is the quantization techniques. So that's actually what we use in production. Is we have an in-house solution that uses a technique called product quantization to do approximate nearest neighbor search of high dimensional vectors and with sublinear storage cost and sublinear query time. Neighborhood graphs have also caught on quite a lot. You see them in a lot of open source or search technologies. I'll talk about those in a little bit. Locality-sensitive hashing was like the flavor of the week about 5 to 10 years ago. Everyone was using this for approximate nearest neighbor search until that product quantization paper came out. So we use product quantization. I want to give a quick overview though, so that everyone can kind of get a flavor of what's out there. If you want to play with approximate nearest neighbor search in your own projects, there's a few good packages out there I highly recommend. If you want to do product quantization on billion scale data sets, check out Fast. It's from Facebook. Super fast. It uses your GPU. It uses that product quantization I mentioned to get going. If you need something a little bit smaller to just get going fast, check out the Annoy package from Spotify. It's really good, super easy to use, Python, C++ interfaces. Also, it's just really good for prototyping, stuff like that. If you want to go at a scale, though, Elasticsearch now supports approximate nearest neighbor. It uses small world graphs, which is cool, but Elasticsearch is distributed, so it's a great enterprise choice. They didn't have this when we built our solution. Now it's regularly available. If we were to build it again, we'd probably use Elasticsearch. And Bolt's another cool library. That's a new kid on the block. Just came out, and it's claiming like really good accuracy measures, but you'll have to engineer it yourself. Okay, so that's approximate nearest neighbor. I want to show how we got approximate nearest neighbor represented in the Arize platform. So here's a copy of the code where I set up the schema. You notice it's pretty simple, right? Like I'm naming my prediction IDs. I got a search ID because we're doing a rank metric there. I set a lot of tags. We'll talk about that in a little bit, including location. And I give it a relevancy score. And you'll notice I'm not setting any features. It's because our feature is really our feature input vector, which we can set up as an embedding if we want. I'll talk about that in a little bit as well. I just wanted to show that this was like a quick piece of code, not hard to set up. And logging the observations was also really easy. So between these two slides, I think I have maybe like 20 lines of code. Took us no time at all to get this model set up in the platform. So once we did, we sent over our reference data set, and then we started sending some live observations. And we wanted to know kind of, hey, how this thing is doing. We had a theory that the models had drifted since we built it 5 to 6 years ago. And every time we used the tool for a demo, it didn't quite work as well as it used to. So we put it into Arize to see what was going on. And oh man, did it get bad. So here I've set up here I'm showing the performance tracing that you get in the Arize platform. And I've set up our key performance metric as recall at 5, right? Just like I talked about. You'll notice our validation set shown on the second line there in pink or in purple is 55%, which, okay, that's not great to begin with, but we thought it was pretty amazing given how hard the problem was. And if we can save our clients time, half the amount of time, we're winning. But you'll notice our live measure at the top is only 20%. It's down 60% from our reference set. This was not the case when we launched it. When we launched it, we did an initial data dive to make sure it was working about 50 to 60% of the time. So we've had something serious has happened here over the last couple of years. We knew that something was wrong, and we wanted to dig into why. Before I dig into why too much, though, I want to show some high-level insights we got just from having that long list of tags I showed you. So if we go down here to the tag section, you can see there's awesome. Expand one of them. You notice I included the client ID in there. This is really cool because we can dig in and see that some clients are getting higher accuracy than others. It really helps us understand the business impact. And it also will help us see like, hey, if there's a new client we onboard, oh, maybe they have a different use case. Maybe they have a different kind of product set that we hadn't accounted for in our training data. You can go back and add that in and get them higher up. So this is really cool. And you only see a few clients here because I only had this running for like 3 days. So again, we're a new Arize customer, but I was excited to share this. Similarly, we can also track what industry they're in. So we have 2 industries we support in this model right now, home goods and apparel. We can see that our apparel model are doing much better than our home goods model. It's helpful for us to know which one to invest in first as we go about fixing these models. We can also look at accuracy by what type of object was clicked. This is pretty cool. We can see that the shirts and dresses are getting high accuracy while tables, beds, and sofas not doing so well. So it's kind of telling us, okay, home goods isn't working out very well. So to sum this up, we got our insights into our ranking model. We saw that accuracy has drifted. We saw that home good models are performing worse, and there's a wide variability across clients and object types. So the natural question that we're going to ask is, well, why? What's going on with this system that we've had so much drift? And to understand that, it's helpful to back farther up into our architecture. So specifically, next I'm going to look at this embedding model. This is where most of our actual learning occurs. Remember, the ranking is just a nearest neighbor measure. So let's talk about some image embedding. This is where it gets really fun. So image embedding assumes that those query vectors are close in Euclidean space. And this is actually a really hard problem because in user-generated content, the products are taken in any number of conditions, whereas in the reference images, the products are taken under nice white lights, right? So our question was, hey, we have thousands of product tags in our database. Can we leverage one client's to improve another one's results? Can we learn the types of changes that the products can undergo in the UGC and then leverage that to make it accurate, right? So we did a big lit survey. We found a promising technique called deep metric embedding. And if you think about the space of those feature vectors, the product matches are probably farther apart than we want them to be. We want to get them closer. So deep metric embedding learns to move correct images closer and incorrect images farther apart. So this is done as a deep learning step. Let's take a closer look at how this works. So first, we take an off-the-shelf pre-trained network. ResNet's good. Chop off the final layer, get that high dimensional vector we mentioned. Then we project that into an embedding space. And then we retrain the network using a special loss called a hinge loss that does that motion that I just showed. It's pretty cool. And when you do that, products that are similar get closer together. This is a visualization from the Stanford Online Products data set. You can see like we got some of the cabinets closer together and some of the pots closer together, things like that. So we did this on our data. We trained the product step, the product matching pairs, and then we uploaded it to Arize. Again, pretty simple schema. This time we're including in the embedding vectors though. And doing the logging, we technically set it up as a classification problem. That's okay. That way I'll show you why we did that in a little bit on the next slide here. So let's look into the platform here. So here you can see on the bottom, we have the object type again. And you can see that, okay, like we have a different distribution going on there. We had more shoes in our model baseline than in the other ones. You can also see that we have some drifting off the bat at the top. Let's dig in deeper and see what's going on. If we hit that UMAP feature, we can look at the from the vectors of our model baseline. We can color them by the object type that was detected. You can see there's no naturally occurring clusters, suggesting that our embedding network isn't a good discriminator for different product types. This can be seen even clearer if you click into one of the clusters. You'll notice the colored labels on these are different. So like one's a shirt, one's a skirt, one's shorts. Again, the embedding network's not doing its job on the reference vectors. Fixing this could yield better results and a more intuitive product. This is a great insight for us. We can do the same analysis on the query vectors. Remember, these are UGC images. So of interest is if the UGC images appear to be clustered better. This is kind of interesting to us. We thought this was cool. If you click into the cluster here, you'll see this. Like all of these shoes are black and white, Adidas striped kind of shoes, right? That's pretty cool. That was interesting to us. If you look at another cluster, you can see the same kind of thing. Here you'll see a bunch of work boots getting clustered together. So our take homes off this one, this was a fantastic insight for us to find. Immediately obvious using the observability tool. Just a few clicks and we saw that, okay, like our reference vectors are too far apart, gotta fix that. And our query vectors are kind of closer together, but could still be a little bit, could still work on a little bit. So I hope I've convinced you that observability is easier than you think. And don't worry, they actually did send me the Arize hat that I wanted at the beginning of this talk. But we saw with only a few simple lines of Python code to onboard, we could immediately see model imbalance issues. In addition, the drift measurement was out of the box, confirmed our suspicion that something was off in the embeddings, and then we could dive in and find the root cause. Fixing those root causes can yield better results. And finally, one thing I didn't talk about too much, we use the platform to measure our actual model performance, that we call it K, of products for our clients. This is awesome because I can share a dashboard of that with my PM, executives, anyone who needs to have observability into that to know how well that product is doing in production. So this is a really big deal for us because it means that I can just share live information to my coworkers off the bat, and they can kind of know how much value our system is adding without having to ask me. It's pretty cool. So the biggest takeaway, though, for me at least, is that I have a lot of work to do fixing up this system. So thank you guys for the time, and I'll take some questions. I think I went 1 minute over. Apologize for that. Cool. So I think I got a started one here. For Elasticsearch, I heard stories their implementation on Approximate nearest neighbor is not as efficient as other players like Fast or Milvus. Yeah, so I think that's because they used small world graphs, which does not compress the vectors. Fast uses product quantization, which does, so you get a much faster result. The trade-off there is like, if you're building a production system, you probably don't care as much about compression because Elasticsearch is dumping all those documents into search indexes on distributed disks anyway. You really care about like what product can you deliver. So that's a really good question. I will sacrifice the disk storage to have something else manage that distribution for me. I had to build that whole product quantization one from the start. So great question. You always have those trade-offs. You should think about when you're doing your project, like, is this a production system that needs to scale infinitely and be distributed and have reliability? Or is it something that is this a one-time data analysis thing or a data pipeline that I don't need that scale, but I need the query speed to get my answers? Cool. Any other questions? Just drop them in the chat. Okay, I'm going to tell myself that there are no other questions because I did such a good job explaining things. Awesome. Thanks again, everyone, for the time. If you drop a question in the Slack, I'll be sure to answer, but I will be delayed by about 30 minutes. Got to pick up my kids from school. So I hope everyone has a good rest. Oh, what's my perspective on combining visual search and LLM type chat for e-commerce UX reimagination? Karan, I just let's the Slack all the time. I love that idea. It sounds really cool. I think visual search has a big place to play in the generative space. In terms of e-commerce UX reimagination, like we live and breathe e-commerce. That startup I worked at, Curate, our whole thesis was to get the visual stuff onto the page to redesign that UX. So really making it pop instead of that kind of boring page you see all the time. So I'm on board. We don't index across all. Oh, CC Gong asked if we index across all of Instagram. We don't. We have the brands authenticate with us, and we use their authentication token, and we can track some hashtags with that. So we do see a lot of volume, but we don't index the whole thing. We see hundreds of millions of images a month, but we get quite a bit. We haven't looked into visual search yet, like Blip. People have been asking me for that at work, so I'll probably get to it soon. It's on my to-do list. Got to fix the image search, I guess, first. The legality. Oh, good question. There's another question about the legality of thousands of white dresses out there. So how do you get it brand specific? Yeah. So as I mentioned, the brands authenticate with our software and then track their own hashtags. So Nordstrom will track hashtag Nordstrom. So the user who's posting the content typically identifies the brands in the image. And then when the brand goes in to tag the products, we still have that user in the loop. They're confirming it's the right product. Our clients are doing it. So is it possible that like a client could tag their product on an image that contains a competitor's product? Probably. It's certainly possible. They have an incentive not to do that, though, because if they post that on their website, like someone's going to call them out. There haven't been any legal repercussions of that as far as I know, but it certainly is something that the brand wouldn't want to do. And because they're looking for their own hashtags or looking in mentions and tags, they typically have a good sense of their audience there. So you certainly have influencers who mix and match different brands, but they often say like, hey, this shirt is from Anthropology and these shoes are from DSW or something like that. Yes. Oh, one other question. Good question. Do they get permissions from the user to post? Absolutely. Our software helps automate that. So when the user posts, hey, at Nordstrom, I'm wearing Nordstrom's dress or something like that, our software posts a comment on behalf of the brand that says, hey, we love this photo. Could we use it on our website? Reply #agree if you agree. If the user replies #agree, we monitor that as well. And that is when the brand will actually go in and add the pictures. So yeah, there's no, our software is meant to facilitate that relationship between the brand and the consumer, certainly not disrupt it or subvert it. We don't want any brands, upsetting their audience. So that's a good question as well. Awesome. I'm out of time. Thanks so much. Yeah, that's what I was saying. They do get the permission from the users to post. So they say like, hey, can I post this on my website or something like that? And if the user says #agree, that's the permissions that needed. So I'm out of time. I really appreciate everyone's questions. If you have further questions or I didn't get to one of your questions, please drop it in the Slack. I'll be slightly delayed. Got to go pick up my kids, but I will definitely get back to them in about half an hour. So thanks again, and everyone enjoy the rest of the conference.